Okay, we're going to talk about hurricanes and satellites and tropical systems and how they're different. Uh, this is Ian on satellite images. This is when it first developed. And I wanted you to notice how not exactly you can see a circulation and all, but really not a lot going on, is there? A bubble here, bubble there, and all that. It's just beginning to develop there. Now, as it goes, it begins to develop an eye as it went across Cuba there. You can see it more plainly. And then it really develops a much better looking eye as it comes into South Florida there. And then it goes away again as it moves across. So, and there's actually some hint of an eye and all off the coast of South Carolina there. So here is some radar imagery as well from that time, and some satellite looking at it in terms of infrared. So you can see the cloud tops gradually growing with time. One of the things I want you to notice the bands out here. You can actually see several new bands developing out ahead of this with time. And these bands are where you may get a tornado. And notice how they spiral in, and then they get very concentric and almost completely surround the eye with very high clouds. And that's what happened with Ian. That's why it became so powerful. So we know hurricanes require warm water. Well, Gulf of Mexico supplies that greatly. Notice how quickly weakened, too. It lost its warm water when it went across land. Even though Florida is relatively small in size as it's going across, it really impacted the storm. As you can see, air got into it and everything with time. So it's kind of a neat image to look at this with time here. So rather than continue with that image, I just thought I wanted to play that for you. And then look at something that's actually going on today. This is an image on satellite of a potential tropical system. It's out over the tropical Atlantic right now, well in the middle of nowhere pretty much. But you can see a little circulation there, some bubbly clouds and all beginning to develop. As of now, it is not even a closed low pressure system. A closed low means winds have to be, you can actually see a circle of winds within the system, but we don't have that at this time. But there is fairly light wind shear. The water temperatures are fairly warm out there. So it's an area that could develop into something. So you'll have to see if you hear something in the news about a tropical system developing in the next few days, well, you'll have seen it before it ever had developed, really. This is what the beginnings of it look like. So with that, let's look at tropical. So what are some of the conditions and all? Well, first off, anything in the tropics is going to be where the sun directly comes overhead. So that means it's between the Tropic of Cancer and the Tropic of Capricorn. And there's going to be little seasonal variation in the weather there. Basically, it has high temperatures, 80, 90s, very humid because there's lots of water down at that latitude, and very little diurnal temperature fluctuation, even from month to month. For example, the lowest temperature, no temperature has ever been below 60 degrees in San Juan, Puerto Rico. So think of that as highs in the 90s, even nighttime lows in the 70s or 60s, and that's it. No fronts pass, nothing. The air mass is very warm and humid. Along there, we talked about the intertropical convergence zone. Well, there's that tropical convergence zone is where the winds from the southern hemisphere and the northern hemisphere kind of converge. Along that, you get thunderstorm developing activity. And that is why, as that moves north in our summer, more and more rain falls. in islands like Puerto Rico, the Virgin Islands, because the intertropical convergence zone has moved north into that area, allowing more thunderstorms to develop. In the wintertime, it moves south into the southern hemisphere, and with that, we have less activity. So a hurricane is basically a cyclone that originates. It's a warm core cyclone. We talked about extratropical cyclones. Well, extratropical cyclones have very high temperature contrast, get stronger with height, and they get colder with height. Hurricanes, warm core, they get warm, they're humid air masses, they have no temperature gradient whatsoever, and they actually weaken with height and may become an anticyclone aloft. You can see the eye here, and we showed you some of that in the imagery I showed you from Ian. And there's an eye wall here you get into sometimes, and storm chasers, Hurricane Hunter aircraft fly into that eye wall and through it. And sometimes described as literally like a stadium effect. And eyes can be anywhere from a couple miles across to as much as 40 to 60 miles across. So you can see there's a pretty good range for size of these. The worst weather is in the eye wall, right around the interior of that hurricane. So here is an actual look at hurricane. You see here, the air descends in the middle of the hurricane. Descending air is warming air, right? So the warmest temperatures in a hurricane are actually in the eye wall, in the eye itself here, where the air is descending. Notice how the air is spinning in, and notice the spirals. There's one band of clouds, another band of clouds, might be more and more intense clouds. As you get closer and closer to the eye, the thunderstorms, the rain, the wind, all becomes more intense. Having now been through a few hurricanes here on the East Coast, it's interesting to watch because as they come towards you, you will get one of these spiral bands, and you'll see it on radar, a line of showers. All of a sudden, that moves through your area. Then a new line forms and moves through your area, and so on till you finally get into the main heart of the storm. So that is something that's interesting about hurricanes. What are some necessary conditions? They need high sea surface temperatures, greater than 80 degrees at least through 150 feet. So that's why the Gulf Stream is a great place for hurricanes to develop or intensify, because the Gulf Stream is relatively warm. Oh yeah, they need a significant Coriolis effect. Well, we know the Coriolis effect goes to zero as you approach the equator. So guess what? You don't get hurricanes by the equator. That's places like Aruba, Curacao. All of that area down there gets very few, if any, hurricanes. We need weak winds aloft when they first form, where we talk about wind shear to help thunderstorms develop and get more intense up in our latitude. Where a hurricane forms, we want relatively weak wind shear, hopefully none. And it needs to be very humid, a tropical humid air mass. So you can see here like the warm water and the cores that go off. Notice all the warm water over in the Gulf Stream, just off the East Coast. Kind of comes up right along the outer banks, gets close, and then moves out the shore. Sometimes you have a hurricane, and you're going to talk about it with Sandy. Sandy came up from the south, moved across the Gulf Stream and intensified, then hit the cooler water and began to weaken a little bit. So that is something that's unique to the east coast of the United States, that Gulf Stream. In the Gulf of Mexico, there is a loop current, which can be extremely warm, and another eddy in the western part. And right now, some of the hottest temperatures on record are out in this Gulf. Winds are always weak when they initially form. They form clusters of thunderstorms, these systems. And these thunderstorms develop gradually more and more in a circulation. During El Nino, which we're in right now, we can have pretty strong winds aloft. What that means for hurricanes is they should become less frequent. However, we have such very warm water temperatures. The two are offsetting each other right now, so it'll be interesting to see how the year progresses with the strong El Nino, stronger winds aloft, but yet very high sea surface temperatures. Here are some averages. Interestingly, over the globe, there's almost 85 tropical cyclones every year. And there's actually a few more tropical cyclones in the western Pacific than there are in the Atlantic. And you can see a map of where they begin to develop here, some favorable regions. And most frequently, because the water temperature reaches its warmest later in the year, September is the prime time for hurricane development. Notice how there's some July, even June, even in May. But boy, they really ramp up in August into September here, and then they begin to die back off. And you can see that when they form too as well. Most of the early season hurricanes form in the Gulf of Mexico or maybe near the Gulf Stream. But then they gradually begin to have more and more of these waves that come off of Africa, the easterly waves that develop. When they begin to develop in the middle of the Atlantic, that's the stronger hurricanes many times. Now, the Gulf of Mexico can produce extremely strong hurricanes as well. But if you're looking at it for the east coast of the United States, they tend to develop more in the middle of the Atlantic and move towards the eastern U.S. And here you can see an easterly wave. Interestingly, an easterly wave has most of the precipitation. Convergence develops on the backside, so towards the east, literally, of the wave, on the eastern side of the wave, not the western side. Saharan air layer. We talked about it a little earlier in the course. What happens is there are dry thunderstorms that developed over the Sahara Desert in the summertime. When they do, they kick up a lot of dust, hababs, you would say. And that air goes aloft. What it does, it's very dry, very stable, very dusty. So as it moves over top of the ocean, well, the ocean layer is really warm underneath it. But it's also more moist, so it tends to be a little cooler than this really hot air that's come off of the Saharan desert. So you wind up with a temperature inversion, so you get more stable air. All of this tends to kill hurricanes or keep them from forming. So we look for the dust clouds coming off of Africa and going across the Atlantic to see if they might impact hurricane development. So here you can see the progressions. Tropical depression is the first one, 23 mile an hour or greater. And it has to be a closed circulation. So it can't just have winds, on the east side of the storm, it looks like the winds are turning around it, but then on the west side, maybe they go in all different directions. You want a full circle of winds all around the storm. Tropical storm is a little bit stronger. That's where we name a storm. And finally, hurricanes reach 74 mile an hour. Interestingly, the worst deaths from hurricanes caused by storm surge. That's what happened during Ian last year. Ian developed a very strong storm surge on the south side of it. Why would that be? Well, think about it. The rotation around the storm is counterclockwise. So that means the south side of the storm had winds coming from the southwest. If you're on the west side of Florida, southwest winds are coming right into the coast. So that pushes the water right up the coast and into there. You can see other hazards. Sometimes Harvey brought great rains into areas. There was a hurricane back in the 1960s called Camille that developed. It actually dumped 30 some inches of rain in 24 hours over the Appalachian Mountains in Virginia and West Virginia. All these are accompanied by a tremendous amount of moisture. How do they get such strong winds? They get the strong winds because there's a very strong pressure gradient. The isobars on these things are almost next to each other. They're very tight. Now, once they come inland, winds diminish because the landfall kills them. Remember, you're not getting the heat from the ocean anymore. Storm surge, though, is just an area. The winds push the water into the coast, gradually piling it up higher and higher to where it eventually reaches ridiculous height, sometimes over 20 feet high. And here you can actually see it. It literally raises sea level. So where you had waves that would be down on the coast, breaking, now they're coming up, starting to break 15 to 20 feet higher. Well, if you're a house and you were 10 to 15 feet above sea level, well, guess what? All of a sudden you have waves breaking on your house. And you can see here, Camille was one of the worst, ridiculous storm surge. Guess what? Sandy, which you're going to tell me all about, had a record storm surge of 12 feet at Kings Point, New York. That is a really high storm surge for that area. The slosh model is a way we do use in the Weather Service to forecast storm surge. It's actually gotten fairly more and more accurate and more detailed. We actually are starting to look at areas literally 1 to 2 miles across to predict storm surge. So there we go, the Atlantic multi-decadal oscillation, where it's been cold back in the 60s and 70s. Guess what? There was hardly any hurricanes. Now we're in a warm phase, and it just keeps continuing, even getting warmer. So there's more hurricanes. El Nino definitely has a trending on them. And we're always looking to see how things are going to change in the future. Interestingly, if the world warms, supposedly from global warming, then starting in about 2050 or beyond, we would definitely see more stronger hurricanes. Not more hurricanes, but stronger hurricanes. So that's about it for this. I wanted to also mention that we do get tornadoes with hurricanes. Why do you get them? Land causes friction. If you get friction at the low levels, you get a strong wind shear because the winds aloft haven't slowed down. So you develop a strong wind shear. And these thunderstorms, which are all around a hurricane, then can begin to spin because of that wind shear, which develops hurricanes. These tend to be far away from eye walls and more to the east side of the storm's motion. So, hope you learned a little bit about this. Let me know if you have any questions.